Good morning, everybody. As I have my first sip of coffee, it's time to do our last lesson on circuits. So today's lesson is going to be on Joule heating and power transmission. And in this story, we're going to pretend that we run an electric company, a competitor to Southern California Edison. So let's just say that we are busy providing electricity to Los Alamitos and nearby points. And we've decided that we're going to do it in the traditional way. We're going to provide 120 volts, AC of course. And somebody in our neighborhood wants to dry their hair. So they turn on a hair dryer. The problem is that our power lines have a little bit of resistance. All power lines do. Copper wire isn't perfect. It's not super conducting. So let's just say that our power lines have a 1 ohm of resistance. And I'm going to put one single 1 ohm resistor there, but it's actually happening throughout the lines on the going and coming back part. And this is going to be a 1500 watt hair dryer. So the very first thing we need to do is we need to figure out what is the resistance of this 1500 watt hair dryer. And so if I was a manufacturer of a 1500 watt hair dryer designed to be used on a 120 volt line, I could use the equation that power equals voltage squared over resistance. It's one of the power formulas. Remember, power is current times voltage, but then you can replace it with voltage squared over resistance, or the Joule heating formula, which is current squared times resistance. This is the one we're going to be using quite a bit today because this is referred to as Joule heating. So let's find the resistance. That means that the resistance of my hair dryer is going to be voltage squared over power, 120 squared over 1500, and we'll get the old handy dandy calculator out here. 120 squared divided by 1500. Okay, that was really unexpected. 9.6. So the resistance of my appliance here is 9.6 ohms. Okay, there's a simple circuit. We can work out some things about this circuit. We can say, oh yes, well now the total REQ is going to be 10.6 ohms, one from my wires and 9.6 from the hair dryer. And that means that the current that's going to flow is going to be 120 volts over 10.6 ohms. Or 11.3 amps of current is going to flow, which is all fine and dandy with the small exception that my wires are going to heat up. And my wires are going to heat up, and I'm going to lose some power, I squared R. That's going to be 11.3 quantity squared times my 1 ohm of resistance. And let's try that out. We're going to square this number. 128 watts. So all told, if I provide power at 120 volts and my wires have a resistance of 1 ohm and somebody plugs in a 9.6 ohm hair dryer, I'm going to lose 128 watts, and we're going to provide them with 1500 watts. So I'm going to have to burn enough coal or crude oil or whatever I've got here. 1628 watts. I'm going to have to actually cough up extra power to provide them with something at their house is only using 1500 watts. I'm going to have to cough up 1628. And this is a losing proposition because, of course, in any given house, it's not just one hair dryer. They've also got lights and heaters and other appliances turned on, refrigerators and whatnot. And I have thousands, if not a million homes. Okay, not a million, not in Los Alamitos, but thousands, tens of thousands of homes that I am providing power to. So this little extra amount that I have to provide is really killing me. So let's do this again. Only now let's go to the absurd extreme, a dangerously absurd extreme. Let's assume that I decide I'm going to fix this problem by providing people with 1,000,000 volts. My wires still have 1 ohm, but now that 1500-watt hair dryer is going to have to be a little different. So 1 ohm of resistance in my wires, and now a 1500-watt hair dryer is connected to this circuit. Once again, we have to figure out that the resistance of this hair dryer is voltage squared divided by power. That's going to be 1,000,000 squared divided by 1500. 1 exponent 6 squared divided by 1500 equals, oh my god, that's a lot. 1, 2, 3, 4, 5, 6, 7, 8. 6.6 or 6.7 times 10 to the 8 ohms. Well, it's not unheard of, but because of the high voltage, in order to only consume 1500 watts, this thing is going to have a whole lot of resistance. All right, there we go. The nice thing about this is it makes the math easier. REQ is just 6.7 times 10 to the 8 ohms. If you add 1 to this, it doesn't show up in any decimal place that we can see. So there you go. And that means that the current that flows in this circuit is going to be 1,000,000 volts divided by 6.7 times 10 to the 8, or 666 million ohms. 1 exponent 6 divided by 6.7 exponent 8 equals, oh my god, it's 1.5 times 10 to the minus 3 amps. Large voltage, really tiny current flowing. That means that my losses are going to be very small. The loss in the power lines, I squared R, is going to be 1.5 times 10 to the minus 3 squared times 1, which is going to be 2.2 times 10 to the minus 6 watts. So essentially, I'm only going to have to provide 1,500 watts if I do so at 1,000,000 volts. Okay, downside. 1,000,000 volts, very dangerous. Turns out that the breakdown voltage for air is about 1,000,000 volts per inch. That means that 1,000,000 volts will throw sparks over an inch through air. So as you go to plug something in, when your hand gets within 1 inch of the outlet, electrical discharge goes into your hand and shocks you, possibly killing you. So this is not a good thing to do. So we do a hybrid. We use very high voltage to travel long distances, and then when we get close to the house, we bring the voltage down to a reasonable level using the magic of a transformer. So this is what the power grid or power transmission looks like. Cartoon version. First of all, we have a very big building with some cooling towers, and this building says SCE on it, and it manufactures electricity, and that electricity goes up to some very tall skeletal transmission lines. And these guys carry nearly 1,000,000 volts. I think the number I heard recently was 760,000 volts. These big power transmission lines, you can see them heading up adjacent the river. I believe it's the San Gabriel River, isn't it? Oh, it's over there. It divides Rossmore from Long Beach. You can also see them crossing the city. If you go north into Cerritos, you can see that there's a line of parks, and those parks have big power transmission lines going through them. So these carry the load for large communities and at a very high voltage. When it gets into your neighborhood, it comes down into a substation. Now, substations are not in a building. What they are is they're these giant aluminum frames with transformers underneath them. And there the voltage is stepped down. Step down to a lower value. And there it goes to wooden poles that you have in your neighborhood. And on some of the wooden poles, you'll find that there's a transformer that brings the voltage down even further, and the power lines are lower. These are at about 1400 volts or so, approximately. And here it's brought down to 240 volts, and that is what feeds your home. Here we go with the third grader's idea of a stick figure house. The person outside, hello. And 240 volts goes to your house. So this is a safe level of current with some losses in these lines, less losses in these lines, and almost no losses in these lines. Now you'll notice that the larger the voltage, the higher above the ground the wires have to be, and that is for safety purposes, because if the air is wet or something, the breakdown potential, the breakdown voltage is much lower than this 1,000,000 volts per inch, and so we could have some arcing that goes on. So we keep those far away from the ground so that we don't arc to the ground, that we don't zap to the ground. Okay, so this is what happens, and the reason why we use high voltage, because that means low current for the same amount of power, and that means less loss to heat, because Joule heating is the phenomenon whereby current flowing through something that has any amount of resistance at all causes that thing to heat up. You might have seen this a little bit in our lab we did. Okay, I'm going to show you a couple more videos that have to do with that. Meanwhile, we're going to transition and talk about magnetic fields from now on.